Hello, so my name is Ashish Kodipati. I am a fourth year CS major at the University of Utah, and the project I'll be presenting today is titled BoTM, Base Station on the Move, a Radio Access Network Management Primitive. And so I will start with some introductory material, and so here's the problem setting. So first off, the softwareization wave has altered network realization. And what I mean by this softwareization wave is mainly software-defined networking and network function virtualization. So software-defined networking refers to extending programmability within the network. And so, for example, you could think of something like OpenFlow, where you can configure how packets are processed within the network in real time through these software tools. And the other idea, network function virtualization, primarily refers to the decoupling of hardware from the network functionality. So you could think of these network functions being able to run on generic commodity hardware, such that it enables these network functions to be rapidly deployed, removed, or moved around um, based on commands dictated in software. So, in a sense, that there's this malleability and extended programmability within the network. And recently, these key ideas have been extended to the radio access network. And because of this, these new paradigms, we assert that new opportunities for network operations emerged. And specifically, we present BoTM, which is this notion that you can exploit network function virtualization to dynamically move a base station to a new location and or piece of spectrum. And so here's BoTM at a high level. So we have these two UEs connected to a base station over a specific band Y. And so what we'd want to happen is we'd want to move this base station to band X along with its UEs, such that the UEs experience uh, very little overhead, and in an effort to make this transition almost transparent. And so here's an animation to illustrate this idea. So we take the base station and its UEs and move them to band X in conjunction. And so how would we realize this, and how would we implement this? And I will explain this in our architecture section. So here's the architecture of BoTM. It follows a generic SD-RAN architecture. And so we have the main components, the MANO controller, the RAN controller, these BoTM agents, and a virtualized infrastructure. And I'll discuss each component in the following slides. So at the very top level, we have the MANO controller. And the MANO controller is responsible for overseeing the RAN lifecycle. And this is at the core of BoTM. Essentially, because the MANO controller is responsible for managing the RAN topology and these non-real-time control functions. And what this means is that the MANO controller is essentially in charge of deploying base stations, or removing these base stations, so therefore molding the RAN topology, or dictating what sort of transmit bands will be used, or which base stations get which resources. And so by doing this, the MANO controller is effectively delivering policy and lifecycle updates, and these updates are directly delivered to BoTM agents that run over the top of these virtualized base stations. And so what the MANO controller does is it promotes this ability to orchestrate across the virtual infrastructure layer. And this primarily refers to being able to spin up and deploy base stations at will. And mainly in BoTM, we use the MANO controller to signal the RAN to initiate and conduct the migration procedure. So at the next level, we have the RAN controller, and the RAN controller differs from the MANO controller in that it's responsible for real-time management in the RAN. And so you could think of things like managing handovers in the RAN, or managing different scheduling procedures such as max scheduling. These things are time contingent and require very low levels of latency. So in addition, the RAN controller is also situated near to the virtual infrastructure, which makes it a good source to aggregate statistical data that's generated at these base stations. In addition, the RAN controller is also able to house these sort of network functions, For example, you could deploy a load balancing application at the RAN controller to minimize the load across base stations at the RAN. And mainly this RAN controller is responsible for enforcing these RAN policy updates, again, like max scheduling or things of that nature. And so what the RAN controller does is it promotes this level of orchestration across the network functional layer, which refers to the protocol interactions that happen at the base stations. And so in BoTM, we mainly use the RAN controller to dynamically trigger X2 handover. And so at the next level, we have the BoTM agents, and these are fairly lightweight. They run over the top of a virtualized infrastructure or these virtual base stations, and mainly they're there to facilitate communication between the RAN and the MANO controllers with the virtualized infrastructure, and they enforce RAN orchestration updates, and they promote this level of orchestration in the network. And at the very bottom, we have the virtualized infrastructure. And this primarily refers to these base stations that are defined in software, going back to network function virtualization. And so what this promotes is rapid deployment, lightweight and tailored base station instances, which promotes dynamic instantiation and removal of these base stations. And because it's defined all in software, there's this low overhead associated with it, along with rapid deployment, or the ability to rapidly deploy these base stations. And in the next section, we'll talk about exactly how the migration procedure works. And so here is the protocol or the protocol interactions. And so here are the actors. We have the MANO controller, the RAN controller, a target base station, a source base station, and a UE. So at the very beginning, there will be a network event, and this is generic, so it could refer to things like a drop in channel quality indicator, or something more along the lines of a spectrum jamming attack. So when this network event occurs, the MANO controller will make a decision on whether to trigger the migration procedure or not. So when the MANO controller triggers the migration procedure, the first thing the MANO controller does is it talks to the target base station BoTM agent and says, "Hey, let's spin up the target base station." And then the MANO controller will receive an acknowledgement, and then the next step is to trigger the handover to move the UE from the source base station to the target base station. And so the MANO controller will talk to the RAN controller, and then the RAN controller will dictate that this handover occurs, or I guess manage this handover. And so it'll tell the source base station to initiate the handover. There will be some negotiation between the source base station and the target base station. And then once the negotiation is finished, the source base station will then tell the UE to move to the target base station, which once the UE moves, then the acknowledgement will percolate all the way up to the MANO controller. And then once the MANO controller receives this acknowledgement, it'll then remove the source base station from the network. And so that effectively emulates the movement of a UE and a base station from its given position or piece of spectrum to a new position or piece of spectrum. So how did we implement this? So we used the FlexRAN RAN controller, and then we wrote our own MANO controller and deployed it above the FlexRAN controller, giving the MANO controller access to the aggregated statistics at the RAN controller. And the sort of network event that we implemented was a drop in channel quality indicator. In addition, we wrote these BoTM agents that run over the top of OpenAir interface eNode Vs. And then lastly, for the X2 handover, we used OpenAir Interface's X2 AP implementation. So here's a specific use case of BoTM. So in interference management in heterogeneous networks. So heterogeneous networks are this idea that we have small cells and large cells of different radio access technologies, and so this is meant to minimize drop in cell coverage and increase the data rate demands, or meet the increased data rate demands. So if you have all these cells within a macro cell, potentially these cells will be transmitting, and at the same time or near the same time, so there'll be this background interference going on. So currently with heterogeneous networks, there's kind of this lack of programmability. So it's harder to manage this interference. But by introducing BoTM, we introduce programmability, thus creating a more reactive uh, uh, management system. So on the right hand side here is a animation illustrating this idea. So we have the two base stations transmitting on a given frequency. There will be some background interference going on between the two base stations. So we use BoTM to remove the bottom base station, and then we'll instantiate it a new target base station on the best frequency, such that the um, interference is minimized. And so here is our evaluation. So first off, we evaluated in power controlled RF environment. We deployed our microcontrollers and the EPC and the RAN controller on a D430 powder compute node. And then we had two base stations running in the controlled RF environment with a single COTS UE. So our evaluation procedure was fairly simple. So we generated uplink and downlink traffic with the iPerf2 network tool. We then introduced interference in both the uplink and downlink directions with an attenuator. And then we just, when the microcontroller detected the drop in CQI, it then triggered the migration procedure, and then we just monitored the CQI, the bit rates, and the packet loss during this procedure. So the first figure here is a time series collection of the observed channel quality indicator. And so on the y-axis, we have the channel quality indicator. On the x-axis, we have the time in seconds. So at the 9-second mark, we can see this is when the attenuation is introduced. So we see this interference causes this huge drop in CQI. And then we have this small gap in between the 10 and 20-second mark, which illustrates the time to spin up this new target base station. But once the target base station is spun up and the handover succeeds, we see that the CQI is restored and it goes back to its original levels. And this next figure is just the uplink and downlink bit rates. And so it's also time series. So on the y-axis, we have the bit rates. And then on the x-axis, we have the time in seconds. So in the downlink direction, we don't see any impacts on the UE. So that's good. It represents this level of transparency during this migration procedure. But on the uplink direction, we do see a large spike at the time of the handover success. And what this illustrates is this notion of the uh, PDCP or Packet Data Convergence Protocol buffer. So before the UE moves all the way over to the target base station, its uplink packets are cached in a buffer. And so when the UE moves, this buffer is processed at the target base station, thus emulating this huge increase in uplink traffic. And so this last figure is just representing the packet loss in comparison to a standalone X2 handover. And we can see that across the board, all the different metrics are very similar to a standalone X2 handover. And what this represents is that while BoTM has the same sort of impacts as a standalone X2 handover, it does much more in that it has this orchestration component that can be used as a management primitive. And so here are some concluding remarks. So for future work, spectrum migration is a big one, so such that we can move the base station to a new band. In our work, we just move the base station to a new position. Another thing would be dynamic carrier aggregation. So you spin up a new target base station that has carrier aggregation enabled to maximize the resources with the for the UE. Another thing would be load balancing. So you spin up two or multiple target base stations to load balance the UEs, and the last one would be integrating intelligence into the decision process for the migration procedure. So in summary, we've presented this novel RAN management primitive, which enables orchestration across the infrastructure layer and the mobile network functional layer. So this refers to the virtual infrastructure, which is the base stations, and also the network protocol interactions that happen. We've also provided and validated a proof of concept prototype, and in an effort to improve RAN resource management in the context of future generation networks. So that is my presentation. Here are my references, and thank you for your time.